Okay, good morning, good afternoon, good evening for everyone. Depends on where you are. Yeah, my name is Zhongyi Ho. I'm the VP Conference of IEEE CEDA. It's my great pleasure to introduce Professor Rolf Drechsler as our prominent speaker for today. Okay, so I would like to provide some information for all of you. Yeah, because this week is actually the annual, actually it's the third annual IEEE Education Week. So in this week, IEEE actually prepares several very good talk, okay, for all communities and societies. Yeah, so in IEEE CEDA, it's our great pleasure to have Professor Rolf Drechsler as our speaker for today. Okay, so let me introduce Professor Drechsler. Okay, Professor Rolf Drechsler, he received the diploma and the doctorate degree in computer science from the Johann Wolfgang Goethe University in Frankfurt am Main, Germany in 1992 and 1995 respectively. He worked at the Institute of Computer Science, Albert Ludwig University, Freiburg in Breisgau in Germany from 1995 to 2000, and at the Corporate Technology Department, Siemens AG, Munich, Germany, from 2000 to 2001. Okay, since October 2001, Professor Drechsler is a full professor and the head of the Group of Computer Architecture, Institute of Computer Science at the University of Bremen, Germany. In 2011, he additionally became the director of the Cyber Physical System Group at the German Research Center for Artificial Intelligence, aka DFKI, okay, in Bremen. His current research interests include the development and the design of data structures and algorithms with a focus on circuit and system design. He's currently the Distinguished Lecturer of IEEE CEDA and ACM Fellow and an IEEE Fellow. And I think his topic today is very, I think his talk today will answer most of the questions for you, because I think you know that most of existing verification technique will suffer from the unpredictability in their performance. But today he will talk about how to do this in polynomial type. I think this is very, really look forward. Okay, so everyone, please join me to welcome Professor Drechsler. Okay, yeah. So the time is yours.
Yeah, thanks a lot for the kind introduction, and also thanks a lot for inviting me and giving me the opportunity to talk about my research field. And as you already mentioned, it is about verification. Yeah, so ensuring correctness of systems. And it is known that this is in general a pretty difficult task. And nevertheless, I'll show you that under some constraints, in some circumstances, this can be done efficiently. Yes, but before I start, I'll start with a pretty general motivation, because I assume not all of you are experts in verification or even formal verification. And so these days we are using computing systems everywhere. Yes, and for me a very prominent and impressive example is the papal election. Yeah, so whenever a pope dies, a new one gets elected. And what you see here, this was the scenery in 2005. That's a view on in Rome, yes, on the church, yes, and all the people are waiting there. And if you look to the very bottom right to this of this picture, you see a person holding up a cell phone. Yes, and this was in 2005. And less than 10 years later, the next pope got elected, and the situation looked like this. Yeah, and what we can observe is that these days, yes, with electronics, we are really changing the society, yes, the behavior. And if you also think about how your own life changed in the last 10, 20 years, yeah, so how electronics influence the communication between people, yeah, so we really have a significant impact on the daily behavior of everybody. And of course, this, whenever we use this kind of electronic components, somehow we assume that they are correct. Yeah, so we use them in the core, we have the chips, yes, in all kind of electronic devices like smartphones. In many cases also we don't really see them, yes, like modern cars, they often come with 200-300 microprocessors on board. And of course also when we think about future technology, maybe using robots or so, yes, electronic and these kind of components will have a significant impact. And what was driving the development of electronics over the last 40 years is what is known as Moore's law, yeah, so that we have this kind of significant increase in complexity over 30, 40 years, as with a doubling of the complexity roughly each 18 months. That's what means an exponential growth over many, many years. Yeah? And even so, today, it is known that this kind of curve is somehow flattening, yeah, so that we don't have this kind of doubling each 1-2 years anymore, yeah. But nevertheless, we now ended up at very significant complexities, yeah. So while the first computer chips we looked into, as like these Intel chips in the early 70s, they had a few thousand components, what is already not bad, yes, but it was still manageable, yes, and they were run at very low clock frequencies. But nowadays, high-end processors have billion of transistors and run at gigahertz. Yeah? So we have a very high complexity to handle. And now it's the question, how can we ensure correctness? And the, let's say, classical, maybe easiest approach to do so is by doing simulation. Yes, typically these kind of systems can be simulated very efficiently. Yes, by you apply some kind of test vectors, you have some kind of expected outcome, and then you see by simulating this, typically done in linear time, so in very efficiently, then you see whether it was the expected outcome or not. But the problem is, while these systems are very complex, when you simulate, yeah, you typically only get a very small coverage by this. Yeah, so the obtained coverage you receive is very low. I see that there's something in the chat, but I typically cannot read this. So yeah, if you have questions, please ask. So that we can obtain the coverage, yeah, but this is very low. Yeah, so there are also ways of hardware acceleration of this. Yeah, so this is what people do with hardware emulators. You can often get 100 or 1000x improvements, but the coverage that you get is still very low. So you can typically not ensure the correctness then completely. And that's what we want. Yes, we want not only in most cases, but if, for example, in a car where also our life depends on the correct functionality, we really want 100% correctness. And there are techniques that can ensure this kind of full coverage. This is so-called formal verification techniques. They are very powerful. They allow complete verification, but they are known to be very expensive. Yeah, expensive in terms of the resources they require. Yeah, and so there's some kind of trade-off that is known for quite a while. Either you get very quick results, but at low quality, or you get high quality, but then it's very expensive. And so the question is, can we have a compromise? Can we get best results, high quality results at low cost? There's of course something very desirable. Yeah, so because the motivation in general in the following is that we want 100% correctness. Yeah, so we really want to make sure that this is running correct. And since this is a problem of very high importance, it has been studied very well, also from a theoretical point of view. And in verification, we typically have two major problems. One is what is called equivalence checking, that you have an implementation and a specification, and you check whether the two have the same functional behavior. Here it can be proven theoretically that this is a co-NP complete problem. And what means that it's very unlikely that in general you will have a polynomial and fast algorithm for all instances. Yes, because it's kind of, we are not talking here about P equal NP, so we believe that this is not the case. Yeah, but here equivalence checking is one task, and then this belongs more to the combinational case. And also if you have memory elements included, then you have this kind of symbolic reachability analysis. Then the problem becomes even harder you can prove that it's in the Boolean domain p space complete, or also for the word level, if you consider bit vectors, even x space complete. But the goal here of this research is to ensure correctness, to solve these problems. Nevertheless, they can prove that they are in general not polynomially solvable, but how can we do this under resource constraints? And so the classical design flow, and that's one of the, let's say, general criticisms, so is that first you typically design something and then you do the verification after the design phase. So this is not something that you consider verification from the very beginning, but you first design something and then afterwards you do the verification. And then sometimes if you somehow, let's say, you designed the circuit in a wrong way, then it's very difficult to finally verify it. And that's also the drawback of the classical approaches that we have, that you have no guarantees these days that the verification is doable at all. There are a lot of commercial tools that are very powerful. And if you start them on some designs, sometimes they give you a very quick, a good result and show that it works, but sometimes they, in some sense, die. Yes, in some sense, they get stuck and cannot get you a satisfying result. And that is exactly here the unpredictability in the performance. And so often when you start, you do not know about the resources you need. Yes, how long will the runtime be? How efficient will be the memory that is has to be handled? So to overcome this, here I'm talking about polynomial formal verification. So that means that we want to ensure that for given circuit, the proof techniques can be applied, that they are complete on the one hand side, but that they have a polynomial upper bound. Yes, and this, in some sense, this was replaced the classical design-centric by verification-centric strategy. And there's some consequences. This means that this kind of verification, this polynomial formal verification, would be an additional design parameter. Of course, we still want to have efficient circuits. That's in the sense that they are small, that they are also fast. So, but nevertheless, you want to always verify the circuit in polynomial time. But this, you could predict the resources. And of course, then you would end up in shorter time to market and also then a cheaper design if you do not have to do some kind of respins later on. So the polynomial algorithms for, and now we consider first this combinational equivalence checking. So more focus on this combinational part, not sequential, what would be even harder. Of course, that's some kind of mixture of, on the one hand side, you need a theoretical analysis, you need the algorithms, but finally we also implement it in complete, hopefully then also automatic tools. And so when we talk about polynomial behavior, then of course we want to have polynomials of as low order as possible. Because if they have something like n to 5 or n to 10, that's also polynomial, but it's pretty large. So since we deal with very large circuits and the underlying structure is a graph structure, it's also very large. So hopefully we get something linear time or quadratic time. And what is here also very important, so that we do not only want this kind of formal verification for the final representation, but also for all the intermediate steps, so that we can make sure that all the intermediate steps of the verification process are, in this sense, polynomially bounded, and by this it can be done efficiently. Since this kind of formal verification in terms of so-called binary decision diagrams as one data structure was introduced in the mid-80s, early 90s, already then people observed that this kind of intermediate computations is very relevant. So here a picture I took from a paper from the mid-90s, so almost 30 years old, so that where people already cared about this kind of peak reduction. And that in these papers and these early works, it was only heuristically done. It was not proven that you can avoid these peaks, but it was already observed. So more than 20 years back, there was a first work on polynomial formal verification of multipliers based on a very specific data structure, so-called binary moment diagrams. But this was only a theoretical analysis. Yeah, so in the meantime, people studied this kind of proof engine, this kind of automatic engines intensively. And now we have, in the meantime, we have very good understanding where these memory peaks come from. And I'll give you some examples for this now in the following of this talk. First, maybe some kind of, let's say, trivial example that is for those of you who have worked in test and verification before, know this kind of circuit. That's a so-called mitre circuit. And it's pretty easy in the sense that if you want to check whether two circuits, circuit 1, circuit 2, are functionally equivalent, what you do is that you first connect the inputs, that they have the same input stimuli. Then the outputs are connected by so-called XOR chains, and then there's an OR gate at the output. And the XOR typically says, is there a difference? And the OR says, is there one difference, at least one difference at any of these outputs? Yeah, and for this circuit, it holds if the output is constant 0, the two circuits are equivalent, otherwise they are not. Yeah, so this is where the output representation is very simple, namely constant 0 in the best case, while in between you do a lot of computations. But now I'll give you an example where you can easily see in a few steps, yes, where these kind of memory peaks in formal verification come from. And I assume not all of you are very familiar with these techniques in general. That's why I give you a very simple example, and I look at this for multipliers. Yeah, multiplication is known to be a very hard problem for verification in general, but this multiplication is a very important task. I mean, it's used in signal processing, cryptography, more recently in all kinds of circuits for artificial intelligence. And when we look at the formal verification techniques like these decision diagrams, BDDs or so, and many other techniques, they all fail for big multipliers. But there is a technique that is called symbolic computer algebra, and that works very well if, and that's a restriction, if the circuit has a specific structure. This means if the circuit, the way we build the multiplier, has some kind of specific structure, we can easily verify it. If it has some kind of weird arbitrary structure, then this still remains difficult. And this symbolic computer algebra, I'll briefly show to you how it works. And for this, I show you here on the right-hand side a circuit. And this circuit is, and that's what I'm claiming, it's a 2-bit multiplier. Yeah, and it can be right or wrong. Yeah, so this is like, since it only is a 2-bit multiplier, we could easily check this by trying out all the possible combinations. Yes, like it has 4 inputs, so we could simply simulate it with 2 to 4 different test vectors, and then we would see whether it's a correct multiplier or not. Yeah, but we'll now demonstrate how formal verification techniques work. Yeah, and for this we know that here on the word level, set is a times b, so the output vector given here set 0 to set 3 is a times b, and that means set minus a times b is equal to 0. Yeah, so that's the kind of high level specification of a multiplication. So here shown in these colors that set, red is this output vector, and a and b are the 2 input vectors. Later on, of course, in experimental studies, we'll scale this up, yes, but here for simplicity, we keep this with 2 bits only. And now when you have this kind of 2-bit encoding, it means like with the weights on the input that 8 times set 3 plus 4 times set 2 and so on, minus a times b is equal to 0. And this is what is the so-called specification, or the specification polynomial. And now this kind of specification polynomial has to be verified against the functional behavior of this gate netlist. And this is equivalent if we now can substitute each of the internal gates and by dividing this kind of gate polynomials. And this means like for each of the gates in the circuit, there are AND gates, there are XOR gates, we have to substitute this accordingly. Now for each of these, we have these kind of gate polynomials. For an inverter, this is F is here 1 minus A. And what is important, even though the values are all Boolean, we do the computation in an integer domain. Yeah, so that is the difference here. Like also F for an AND gate is A times B. For an XOR gate, it's A plus B minus 2AB. And for the OR gate. So we can, for each of these gates, we have a corresponding formula. And now what we do is that we go from the outputs to the inputs and substitute these gates. Yeah, and this means like for this integer multiplier, the division equals the substitution of these gates. And the core algorithm of these kind of formal proof techniques these days is that you go from the outputs to the inputs step by step, and you substitute these gates. And this is now what we have. This is exactly the formula I've shown before, yes, with this kind of here formula that for the output minus A times B for the inputs. And now what we do is that we substitute here for this G1, that is this cell G1, yeah, and this is an AND gate, so we substitute Z3 with the inputs W1 times W4. So this is just the gate computation I've shown before. And now we go step by step backwards. Yeah, so we have now 8 times, and we describe this here now in terms of some internal signals, and we do the substitution towards the inputs until it is described by the inputs values themselves. And now if we substitute the other gate G2, then we see that there's a term 8 times W1, W4 that appears one time in positive and one time in negative form, and it cancels out. And this is exactly the kind of memory peak that we see in this kind of formal proof techniques. Yeah, so some terms get generated and then they cancel out and get deleted. Yeah, and this is a kind of memory, additional memory that we briefly need. And then at the end, if we substitute, we continue, it would end up with being 0. And this means that this is really a multiplier. Yeah, and that's what we have proven here. And now, if we do this for some kind of other multipliers, yeah, so this is a kind of, I would say, classical textbook multipliers, as you see it in some kind of computer architecture courses. You first generate the partial products, then they get accumulated, and finally they get added. And the way how these kind of multipliers differ is the way how you generate the partial products, how you add up this in a simple array or as some kind of tree-like structure. And finally, you can use some kind of final stage adder for adding this up. So looking at this, let's say the most simple multiplier you can think of is you have the partial product generation. You take an array, given here is AR for array, and a ripple carry adder. And they have the properties that all the intermediate steps only consist of half adders and full adders. And in terms of verification, that's, you can say, verification friendly. For non-trivial multiplier, on the first stage, it's the same. It generates the partial products then. But here now there comes a Wallace tree and a carry look ahead adder. And so they have the properties that the internal signals do not consist only of half adders and full adders. And now if we do this kind of an experimental evaluation, yeah, so we now look at how does the verification, what I just did with this symbolic computer algebra, I go from the outputs to the inputs and substitute, how does it work for these two different multipliers? And what we see is that the simple one, it has this kind of very flat line. Yeah, so for the number of monomials, and this corresponds to the memory, what is internally used. Yeah, so this is almost here only 25 terms, 30 terms at the beginning, and it remains on this level until at the very end, if it's correct multiplier, it goes down to 0. As you see here, for this non-trivial one, it requires twice the number of terms for this 4-bit. Yes, and now we scale the problem up from 4-bit. We now go to an 8-bit multiplier. And you see that, again, for this blue one, for this simple structure, the line is almost flat, while now, it means here around 100 terms. For the 8-bit complex multiplier, we need already 1,000,000 terms. Yeah, so it really explodes in the number of terms that have to be represented at the same time. And this, as I said, corresponds to the memory. And now if we scale this one step further, yes, for not 8, but 16-bit, you see again, the blue one is pretty flat, while the red one goes up, yes, and cannot be represented anymore. Yeah, so, and this means that we have this kind of explosion in the number of monomials, and in the terms of this kind of verification community, we speak here of the problem of these vanishing monomials, that you have to compute some intermediate results, and then they are not needed at the end. And now the question is, can this kind of peak be avoided? Yeah, either we have a simple architecture where it does not occur at all, or can we somehow avoid this kind of peak? And there have been many experimental studies in the past, yeah, to look at this. Yeah, and it turned out that often, yeah, with some kind of tricky techniques also, this kind of peak can be kept down. Yeah, but this was purely experimental. Yeah, so no guarantees that this cannot be further improved. And that is now what I'll show in this kind of polynomial formal verification, that for some circuits, if you have the right circuit and the right proof engine, then you can really make sure that you can have polynomial upper bounds. Yeah, this is not a contradiction to the NP completeness proofs before, yeah, because they only say like there's not one engine that can handle all the circuits. But there's not a contradiction that for a specific circuit, we can also have then with the right engine this behavior. And a very popular technique here are so-called BDDs, binary decision diagrams. And what is the difference to a classical simulation is typically you would apply 0 or 1 values at the inputs of a circuit, while here you apply Boolean variables. Yeah, and by this, you do not a simulation with values, discrete values, but with variables. And by this, you generate the BDDs for the inputs, you generate them for each of the individual gates in the circuit, and then you propagate them to the outputs. And then for the final outcome, you get this kind of circuits. And this kind of internal evaluations, yes, this computation for the gates and the blocks is done by some classical synthesis operations. And for these, it is known that they have some kind of polynomial worst case behavior. Yeah? So that, but here, of course, you have to ensure that also when you iterate this, yes, if you do this for all the internal operation, that it never gets larger than some kind of polynomial given upper bound. And in the first step where we studied this was for adder circuits. For adders, it was known that the outputs have polynomial bounded sizes. Yes, but now we look at this during the construction. Yeah, and and therefore quite a number of adders, yes, like ripple carry, conditional sum, carry look ahead. This could be proven, yeah, that we can have using BDDs. We have this kind of polynomial upper bounds, yeah. And in the first study, it was only done theoretical, but now also implementing all this, yeah, that you do, for example, for a carry ripple adder. Yeah, this was a work in below. You also see the publication, also that you see now we are really approaching the very recent time. Yeah, so this was published a few years back, and then it could be proven that this can be done in a polynomial, in the worst case n to 4. And if you implement it, yes, then you can see that, I mean, for multipliers, we had problems before for 16-bit, 32-bit. Now we can do the computation for 1000-bit in no time. Yes, even for 10,000-bit, it takes a few hundred seconds. Yeah, so this gives a significant improvement then. Yes, and you can by construction guarantee that this works. Yes, of course, adders are nice, but the whole world does not only consist of adders. Yeah, so now you look for more complex structures. Yeah, so but here it confirms the theoretical calculation that this can also be done efficiently. And then once you know how to do addition, you look into some kind of ALUs, yeah, so that you have a very simple ALU there. It has to be said that if you just do BDDs straightforward, as for BDDs for adders, this will fail. But here what you can do is that ALUs, yes, they have a fixed set of different operations. And if you simulate each of these operations separately, what is here then called partial simulation, this can be done efficiently again. Yeah, so this also works for this kind of operations. And now also you want to do this in a more complex fashion. And here that's also our most recent work in this domain, that we applied this to a RISC-V architecture. That's a very popular architecture these days. Yeah, so where you have a configurable instruction set, as for a 32, 64, 128-bit, and you can also have some kind of base instruction, or you can have multiplier and dividers, floating point, and so on. Yeah. So first, what we consider is the very basic one. Yeah, 32-bit with the I instruction. Yeah, and then you can do this kind of partial simulation where you are BDD based. You synthesize this. You convert it to some kind of dedicated data structures where you do the partial simulation and also symbolic simulation later on, and then you compare this with some kind of reference design. And then we also, with a system that we build on our own, the RISC-V in general is only the instruction set architecture, but now you want to also check it versus some kind of low-level implementation. So that's a micro RV32, also a 32-bit implementation of this, yes, with some kind of combinational parts, yes, like the decode and execute and ALU, but it also has some kind of sequential aspects of low depths, yes, where you can use so-called bounded model checking, where sequential behavior can be unrolled so that it becomes combinational again. Yeah, and here the idea is pretty similar, that you have the RISC-V, you synthesize, you use some kind of partial simulation for the fetch, decode, execute, and write back. So similar to how the pipeline structure is typically done, you get this instruction and then you do the verification process. And most recently, we also showed how this can be extended then to this kind of fetch unit on the one hand side and to the control unit with some kind of sequential behavior as well. And this is what very recently got presented at a DATE conference as a few weeks back. So, and where this is somehow currently, we can say, the state of the art. But also to understand a little bit what are the limitations of the approaches. Yeah, so this sounds all very nice, yes, but what are the things that we can't do? Yeah, like we can do this kind of floating or this kind of different operations in the pipeline. But for example, how about floating point? Yeah, so because if you want a full-fledged RISC-V processor, you also have to consider these kind of operations, yes, like floating point, division, and so on. Yeah, and floating point, in general, it can be shown that also symbolic simulation, yeah, for floating point adders, yes, cannot be handled by BDDs in general, but we can show that there with some kind of clever techniques, floating point addition can be handled. But for example, in the multiplier package, also dividers are given. And so far, we don't know how to do division. Yeah, so there's a like currently some kind of greedy approach where we try to understand the different arithmetic operations and provide polynomial upper bounds on this. So in general, yeah, if you want to use polynomial formal verification, as I said before, you can prove that there's not a general solution. So it means like you need some kind of additional information. And this additional information can be, for example, you know about something about the structure of the underlying circuits. Yes, if it's a restricted structure like a tree-like structure, or you know something about the function you are representing, for example, some symmetry properties, this can be used. Or also if you have some kind of hierarchy information from the design, yeah, and then it can also be that there's some kind of hybrid proof engines that might help. Yes, that there are some parts where you need one engine and another one where you need a different one. And so for this, I'll give you one example. Yes, when you have a complex circuit that has several subcomponents, it can be that some of these components, yes, can be used very well with one engine, but there's not a monolithic proof engine. Like not everything works with BDDs or the symbolic computer algebra. Yeah? So sometimes you have to mix the different proof engine, yes, and what we call here this hybrid proof engine, where there are some parts of the circuit that can be very well handled with bit level verification methods, and for other you need this kind of word level embedding for this kind of operations. Yeah, and so to give you an idea of how this works, yeah, so let's consider again this kind of multipliers, since I introduced them earlier. Yeah, so when we know that this kind of clean multiplier that only consists of half and full adders, this works well, but the other ones has some serious problems. Yeah, so for the verification steps, what we can do is that we replace this kind of final stage adder that might generate difficulties with a simple one, and then we do this kind of proof separately. So let's assume again, we have this kind of three-stage multiplier, partial product generation, the accumulation, and the final stage adder. And if the final stage adder is the component that generates the difficulties, yeah, then we can cut this out, put this separate, substitute it by a simpler final stage adder, for example, a ripple carry adder, and then we have to finally do a comparison between the two. And this, of course, then both verification tasks have to be taken into account. Yes, on the one hand side, you look at what is the verification complexity of the simpler multiplier, and what is the equivalence check between the two final stage adders, yes, the simple one and the more complicated one. So this is currently what we are working on, yes, and to also look at alternative proof engines. And I'll also point to one other, let's say, general difficulty, yes, because everything what I showed so far, yeah, was that we had this kind of all the proofs we did were performed manually. Yeah, and of course the question is, can this process, yeah, also be automated? Yeah, because on the one hand side, it's some kind of time-consuming task to prove something by hand, and of course maybe, yeah, so like earlier people worked with theorem proving techniques. It's good to have some kind of protocol tool that checks all your proofs that they are really correct. Yes, and so the question is, can we also automatically prove polynomial upper bounds? Yeah, and that is in some sense that's not let's say totally new idea. Yeah, so there are several other fields where this kind of automatic proof techniques have been applied successfully, as like theorem proving, as I just mentioned, also in some kind of mathematical problems like the 4-color problem, how many colors you need to color some kind of two-dimensional planes, where there were upper and lower bounds known, yes, but finally to enumerate all the remaining cases, yeah, so this can be done easily done by a computer. But the problem is that often the proofs are not human readable. Yeah, so that is like that people do not really trust the proof. Yeah? And here the goal is, can we now also generate human readable proofs, yeah, that gives us polynomial upper bounds? Yeah, so that we have automatic proofs. Is this possible also for polynomial formal verification? And so I'll show you our first steps in this direction. So this is still ongoing work, yeah, so it's not that we have a complete solution here, yeah, but also based on this kind of binary decision diagram structure that I've shown before, yeah. So there you can often prove also sizes by induction, yeah, and we have on the one hand side this kind of human readable proofs, but they generate the proofs, yeah, and then later on also without manual interaction. And the idea is that we can generate some kind of a database, yes, where for each function, like for example, if someone as a designer says, I need a fully verifiable adder or fully verifiable multiplier, or I need this function, yes, and you can look it up whether there's a kind of polynomial proof that is already existing, or the system can try to generate it by itself. And here, the core idea is that we have this kind of input function. Someone says, okay, this is the function I want to have a proof for. Then we have this kind of pattern finding approach. Yes, we say, okay, we use the kind of BDD with k iterations, with a given number of iteration. And when we try to perform the induction on this, either this is successful, then we have the proof given, or otherwise we have to look for alternative patterns. So that's this kind of loop that is given here on the right-hand side. And to show how this roughly works, so we have a very simple example. Those of you who know BDDs or have read the original paper by Brian, this original function that he demonstrated for the influence of the variable ordering. Yeah, and if you choose a good variable ordering, it has this kind of linear behavior. And what we also see as humans, there's some kind of very simple inductive structure, yes, and that's something these tools can easily find. Yeah, so that's the pattern they look for, and by the induction you prove then the correctness of the pattern over this k iteration. So you compare the BDD for the base case. Yes, this is this kind of pattern that you see here on the right, and then for each of the induction steps, then it needs this kind of application by classical synthesis operations, if then else, this operator that I've shown before. Yes, and this also has a polynomial worst case behavior. Yeah, so that's the way how to automate the proofs later on. In current implementation, it looks for some kind of constant size BDDs, this kind of nodes. Then it can generate also in some kind of text format the complete induction step, and in this sense it becomes human readable. Yeah? And of course also looking at what large language models can do these days. Yeah, so we also experiment with this. And of course then it tries to find these kind of patterns, including the induction, and by this generates a proof. So, and once now we have this kind of core technique, yes, there this can be expanded in various ways, yes, like more classes of functions that can be described. Also to do this not only for BDDs, but also different types of decision diagrams, and also including other verification techniques, as it's more for the experts, like here answer set programming or symbolic computer algebra, Kronecker functional decision diagrams. But there is a whole bunch of different proof techniques that can now be studied here in further detail. And as I said, now we set up a database, yes, where then you can link this corresponding proof with the corresponding proof engine. These techniques not only work for concrete, fully specified functions, but also for approximate functions. What means, like, if you have a function that is almost the one that you will find in the database, so it's pretty similar, yeah, it can also be extended. And of course, a real challenge in this field would be, I mean, so far we only built upper bounds, but maybe if you do not succeed to find an upper bound, you can also try to prove an exponential lower bound. And there are also techniques how to automate this process. If you're interested in this field, there on the one hand side is a tutorial paper at ICCAT 22, and also on this kind of generation of human readable proofs more recently at a conference memo code, where the papers are also available on our website, and there you can further get details on how this is done. So the next steps in general is we have for first successfully proven for some circuits, for some classes, that this kind of polynomial formal verification can be done. We want to, and this is the goal of our research work, get a fine-grained understanding of all the combinational equivalence checking tractable classes. Yeah, so what kind of circuits can be handled efficiently? And then for these circuits also to find efficient decision procedures. Yeah, so all kind of proof engines, either existing ones, or also build new ones, yeah, that can then handle the respective circuit. Because that's also what has been done in the field of verification in the past. So sometimes, for example, for floating point multipliers, there had been some kind of very specific data structures that target especially this kind of challenge. Yeah. And of course, then for the designer, we want to feedback some kind of design guidelines, some rules, yeah, that we say, like, if you want a fully verified circuit at the end, you have to build your circuit this way, yeah, and try to avoid this kind of structures, yeah, so that this kind of knowledge about the design can also be included. And of course, we are currently working on some kind of more advanced case studies. As I showed you, we were successful with some kind of RISC-V circuit, but it's a pretty restricted version. Yeah, so now you want to have a full-fledged one. There are many other things to consider. So in summary, polynomial formal verification is a new research area with some kind of first promising results. Yeah, so some case studies where you can see that you have to apply the best fitting solve engine to the respective circuit. And the more far-reaching vision is the correctness by construction, that we have some design for verifiability approaches. Finally, I want to summarize, and especially like to thank my people, yes, who are working with me on this project. The PhD students and also master students are listed here. And by this, I'll conclude and thank you for your attention.
Okay, thank you so much. Wow, this is a very comprehensive talk. Yeah, so I think some of you probably did not know that Professor Drechsler actually gave several tutorials in many conferences. Yeah, so I can tell he already include all, the spirit of, inside this talk. Wow, that's very impressive. Okay, so I do have few questions, but right now we actually have a question from the audience. Yeah, so I think he is asking what are the tools that are used to obtain polynomial equations for the circuit mentioned. Yeah, so Rolf, can you answer the question first?
Yeah, I mean, like, first of all, good point. I mean, we, at the entrance to the tools, yeah, so you always have to convert the circuits in a readable format for this kind of proof engines. And this depends a little bit on the structure of the circuits. Yeah, so because some of these solve engine require some kind of Boolean description, like typical what you have are SAT solvers in formal verification. They work on these conjunctive normal forms. But for this kind of polynomials that I showed, yeah, so there you need some kind of internal polynomial representation. And there some of the tools are available publicly, yes, like these we also used for the RISC-V, like these end inverter graphs. So that's a tool that is distributed ABC, that is by Alan Mishenko from Berkeley. Yeah, so that's a very powerful, very good tool that also comes with a BDD package. Yeah, so with some kind of proof engine included. But of course, when you experiment with floating point or so, sometimes you have to really do the conversion by yourself. Yeah, so there are some experimental tools. Yeah, so also from our group, we have some kind of arithmetic generation tools available. If you, for example, want to generate different multipliers, yeah, so in Verilog netlists, this can easily be done. but then it really depends a lot on the respective proof engine you are using. As long as you work on a Boolean domain with AND and OR and so only, as for using BDD and SAT, there's a rich set of tools available. The more you go on higher levels of abstraction, yes, the fewer tools are there. Yes, but in general, this kind of conversion is rather straightforward, and you can easily do this.
Okay, and there's another question from Sade. Yeah, he mentioned that can we verify the IC regarding non-functional properties like power against a specified threshold by a function formal verification or only functional correctness?
Very, very good point. I mean, what I presented here is purely functional, but of course, we also look into non-functional properties like timing, like power, and then of course, and also what is still a big challenge is all kind of analog mixed signal. Yeah, so whenever you, I mean, here I'm whenever I said circuit, I mean a Boolean circuit. Yes, and so this is something that for analog mixed signal we look into, yes, but then also let's say the underlying models are not that clean anymore. Yeah, so like also when you look into delay, it's the question, do we talk about zero delay, a unit delay model, or what is your underlying delay model? And for some circuits, this might be doable, but so far here in what we mainly did was essentially non-functional properties. Yeah, so only the functionality was done and not for the non-functional ones.
Okay,
but it would be a very interesting research area. Yeah, so that's like in this sense, but this is pretty new here. Yeah.
Yeah, I think the core algorithm and methods can be used for many applications, right? In other properties, and also I think you also apply these for different circuits, right? Reversible circuits, quantum circuits, etc. Right? Yeah, I think they are.
When you look at the literature, also in the early 90s, a lot of people looked into ATPG, automatic test pattern generation. And there also there were papers where people said, okay, under specific constraints regarding cut width of or tree width, some kind of properties of the underlying network, then you can ensure also test generation in polynomial time. Yeah, and these are results that we can also transfer now one-to-one to the verification case. And of course, for us, it would be also interesting to see about our findings. What can we transfer back to other domains? Yes, maybe also the people in test generation, yes, can profit exactly from the same cases. Yeah, but this is also, let's say, a more holistic way of looking at what kind of complex problems, complex in the sense of being NP complete, or let's say even harder, can be solved efficiently, under which constraints, taking into account the respective proof engine.
Yes.
No, but that's a very, very interesting research field.
Yes. So under certain resources, so what can we do, right? Yeah. So, but the resources probably from the time resource or space resource. So talking about resource, do you or your student ever try to use the GPU, right? Try to accelerate, such kind of, because this is very time consuming. I believe maybe you or your students or your collaborator already start to try to find something, could be accelerated by the GPU or something.
In my team, let's say this kind of polynomial formal verification is, I would say, the cleanest approach. Yeah, so that's the nicest one. Yeah, but nevertheless, we still have a whole set of circuits where these techniques do not work yet. Yeah, and of course, in the others, we still use some kind of symbolic simulation to mix regular simulation with symbolic techniques, also constrained random verification. And in these cases, of course, we use GPUs. Yeah, so then is where you also make use of all these kind of hardware accelerators. Yes, these kind of accelerator cards that you can get these days. But this, let's say, different approach. Yes, on the one hand side, if you can do polynomial formal verification, let's say in the best case, you don't need these kind of accelerators, because it's already that fast. But in case you cannot handle it, you're totally right. Then all kind of simulator enhancements are very welcome.
Yeah, I totally agree. Yes. Okay, so do we still have questions from the audience? You can type your questions in the chat box, or I'm not sure if you can just speak out your question. Okay, I think we still have I think we have 3 more minutes. Yeah, I found the room will close in 3 minutes. I'm not sure if that's true or not. Yeah. Okay. Yeah.
Yeah, but thanks a lot for the interesting discussion. So, and of course, feel free to here on the slide, you still see my email. Feel free to contact me if most of the papers, literature are also available on our webpage. But if you have, if you want some further material, feel free to contact me.
Yes, thank you. Yeah, you also mentioned several ongoing work. Yeah, several like the human readable, and some the division is not doable right now. Yeah, these are all the open.
If someone has some good ideas, please also contact me. So we are very interested in this.
Yeah, division. Yes. Yes. Thank you. Yeah, I think all audience here learned a lot from your excellent talk today. And I would like to say, note that this talk is recorded, so maybe after 1 week, and we will put this talk on the CEDA, IEEE CEDA presentation library. Okay, so if you miss something, please look at the video again, or contact Professor Drechsler directly. Okay, so Rolf, thank you. Thank you for your wonderful talk today. I really appreciate it.
It was my pleasure. Thanks a lot.
Yeah, thank you. Okay. Bye-bye. Okay,
Bye.
bye-bye. Yeah, thank you. Bye-bye.